Hey everyone, and welcome. Today we're diving into electromagnetic potential and boundary conditions. But, we're not just going to reread the textbook. Instead, we're going to uncover a hidden, sort of unwritten law of physics that ties all these concepts together in a really elegant way. We'll look at how electromagnetic potentials make complicated things simple, and then we'll see how this hidden rule perfectly explains what happens when fields hit a boundary.
Right, so you're probably familiar with the electric field E and the magnetic field B, but there are deeper things going on here. One of them is the link between quantities based on amperes and those based on volts. But there's a third one, a fundamental rule that's so powerful it actually dictates how all these fields act. And today, we're going to drag it out into the daylight.
Okay, so let's get into this framework. You can see here on the right side we've got our quantities in the ampere system, and over on the left we have the volt system. Now these two sides are connected in what we call a conjugate relationship. Really, just think of them as two sides of the same coin. They're fundamentally linked. And this duality, that's the second attribute we're talking about.
Now this is where it starts to get really interesting. What happens if you take a quantity from the volt system on the left and you multiply it by one from the ampere system on the right? Well, what you get are terms that describe energy or power. For example, if you multiply D and E, you get electric energy density. It's a huge clue that these two systems are woven together, but there's still a bigger principle at play.
And that brings us right to the heart of the mystery. There's a third, hidden attribute, an unwritten law that isn't just some convenient way to group things, it's a fundamental concept that elegantly explains why electromagnetic fields behave the way they do, especially when they hit the boundary between two different materials.
So, how do we even begin to find this hidden law? Well, our first clue comes from a really powerful mathematical tool, Helmholtz's theorem. It basically tells us that any vector field out there can be broken down into two simpler parts. There's a part with no swirl or curl, which we can describe with a scalar potential, we'll call it phi, and there's a part with no source or divergence, which we can describe with a vector potential, A. By using these potentials, we can make our equations a whole lot simpler.
Let's see how this actually works. So if we define the magnetic field B as the curl of our vector potential A, then one of Maxwell's equations, the one that says the divergence of B is 0, is just automatically true. It just works. And similarly, if we define the electric field E using both potentials, another one of Maxwell's equations is instantly satisfied. We're essentially baking the laws of physics right into our definitions. It makes the whole system so much more elegant.
This brings us to a really crucial point, the difference between static and dynamic fields. A static electric field is what we call a conservative field. It has no curl. This is exactly like Kirchhoff's voltage law in circuits, right? Where the voltage around any closed loop always adds up to 0. But what happens when things start moving? When you have a magnetic field that changes over time, the electric field it creates does have curl. In that dynamic world, KVL doesn't really hold up, and that's precisely where these potentials become absolutely essential.
Which brings us right back to our central question. Okay, we have these powerful tools, the potentials, but what's the underlying physical principle? What is this hidden attribute that connects everything from Maxwell's equations all the way to how fields behave at a boundary? And here it is, the unwritten law. We can classify all physical quantities into two basic categories, intensive-like and extensive-like. Now, intensive-like quantities like E and H are all about properties at a specific point, measured along a line. Think voltage drop. They're tied to things like Stokes' theorem and Kirchhoff's voltage law. On the other hand, extensive-like quantities like D and B are about properties over an area or volume, measured through a surface. Think current flow. And these connect to Gauss's theorem and Kirchhoff's current law.
And this quote just nails it. This is why this concept, even if you don't see it formally named in textbooks, is so incredibly powerful. By sorting quantities into these two buckets, the way physical phenomena are distributed in space becomes so much easier to formulate and to understand. It's a mental model that just cuts through the complexity.
And now for the big payoff. All of this theory isn't just for fun. This one idea, this division between intensive and extensive quantities, it's the master key. It unlocks the seemingly complicated rules for what happens when fields hit a boundary.
Okay, let's look at the basic rules of the road, at least under static conditions. For our intensive-like quantities, that's E and H, they're components that run parallel to the boundary, the tangential components. They have to be continuous right across it. But for the extensive-like quantities, D and B, it's their normal components, the ones that are perpendicular to the boundary, that are conserved.
Now let's actually map these rules onto our EDBH framework.
So on the left, you've got the abstract equations, and on the right, we're slotting them into the framework. And look at that. It all fits perfectly. The rules for the tangential parts of E and H, our intensive-like quantities, they're related to curl, which lives on the volt side of our diagram. And the rules for the normal parts of D and B, our extensive-like quantities, are related to divergence on the ampere side. Our hidden law makes the entire system logical. It just makes sense.
So the whole thing can really be boiled down to a super simple two-step process. First, you just ask, is this quantity intensive-like, like E or H? If it is, its tangential component is continuous. Step 2, if it's extensive-like, like D or B, its normal component is conserved. That's it. That's the secret code. So let's just recap for a second. We started with a mystery, and what we found was an unwritten law of physics. This single, elegant principle, classifying quantities as either intensive-like or extensive-like, let us see the deep structure connecting potentials, Maxwell's equations, and all those boundary conditions.
All right, here are the key takeaways from our explainer today. First, electromagnetic potentials are our friends. They simplify Maxwell's equations. Second, we can sort all physical quantities into intensive-like or extensive-like. And third, this classification directly tells us the rules for boundary conditions. The tangential parts of intensive fields are continuous, and the normal parts of extensive fields are conserved.
And that leaves us with a final thought to chew on. This idea of intensive and extensive properties, it's not just for electromagnetism. You see it pop up in thermodynamics with variables like pressure and volume. So the question is, how might this powerful, unwritten law give us a unified way of looking at other complex systems in physics? Thanks for watching.